So good morning, folks. I'm very pleased to be able to speak with you today about microgrids. I'm going to be talking a lot about what they are, how they can be used, why they're important, but I'm also going to spend a fair amount of time highlighting some of the engineering challenges that microgrids bring. Because one of the things that I want to make sure everyone leaves this presentation with is a appreciation for the fact that although power engineers make it design both the large grid and microgrids, the differences between the two are such that the technology, while overlapping, does not just easily flow from one to the other. But before I get started, what I'd like to do is give you just a little bit of history of microgrids in the U.S., just because I think it's interesting. I found it fascinating. In the United States, we started out only with microgrids. This chart that we see here is a picture of the power system that Thomas Edison built initially in the first power system in the U.S., first grid in the U.S., and it was a DC microgrid in Lower Manhattan, following about 10 or 12 blocks in the city. The power station itself just looked like one of the standard buildings along the street. However, we quickly outgrew this for two reasons. Number one, it was too hard to have a whole lot of very small power systems competing with each other because it put too many poles and wires in the city. And number two, and probably the more important one, is the engineers who were working in power systems figured out how they could make the technology to achieve an economy of scale, where I could put the power system, the power plant, well outside the city and run wires from a large power plant running power back into the city. A secondary advantage of this was it provided we invented a U.S. system for how to finance this. So we could basically let the company sell shares, and everyone could put in a little bit of money and get a return on their investment, and it worked for everybody. The technology was right, the financing was right, and we quickly electrified the United States using not microgrids, but a few very large grids. But what had happened is technology isn't smart enough to stop getting better. And what has happened is what used to be an economy of scale allowed the lowest price. There are many, many places now that we have technologies like wind power and solar power that are cheaper at producing electricity than a large fossil fuel fired plant or a large nuclear plant. So we have gone full circle from using the plants and building them because they were the cheapest solution to now being having to amortize those costs, realizing that they're not the least costly solution. And something I'm going to come back to and hit a lot harder later is that as we electrify the world, and it happens at different rates in every part of the world, the reliability of the power grid becomes a very, very significant. When you were only using electricity to give you a few lights at night and to charge a cell phone, maybe that was not if you were out of power for a day, that was not necessarily a major problem. But when it's used for preserving food and for entertainment and for banking and for communication and for computing, suddenly the importance of having reliable electricity becomes very, very significant. And that's one of the reasons why microgrids are growing in popularity today. And I'm also willing to be interrupted at any time with questions. I know the material well enough to come back. I would also want to introduce the fact that the University of Texas, and here's another shot of part of our university, has what is at least the largest microgrid in the United States. It's a 50 megawatt combined cycle generator that powers the campus, and it also provides heat for heating and cooling water for the buildings. The reason we did this was totally financial. The microgrid was not considered a good idea. Microgrid was considered a good investment, and the university has documented it saved millions of dollars by being its own microgrid over what it would have cost to provide the same energy level if we had to buy all the various pieces on the open market. But this 50 megawatt microgrid is the power and the for the whole university. This is not something on which we do research. This is a active uh, supply of power for everything. It does have a bidirectional connection to the local grid, but because we are big uh, on microgrids, we also have a 1 megawatt research microgrid, which I'll be talking about a fair amount, which could work as either be configured as either an AC or as a DC microgrid. This is a one-line diagram, basically, of the an old configuration that we had our 1 megawatt microgrid in, but I picked it out because it makes a point. This is configured to replicate the power system on a ship. And one of the things that turns out for microgrids is that uh, most of transportation electrification is a microgrid. It has a power source, it has a distribution of power, has a variety of loads, it has a power control network. And if you go to things like aircrafts and ships, these can be very significant power systems. And we've done a lot of research and are still doing research on the using the microgrid to understand how to optimize delivery of power in transportation electrification. I should highlight that in transportation electrification, the power density is king. If I'm building a microgrid to take a neighborhood or an industrial park, I don't really care how big the components are and how much they weigh. If I'm going to put them into a car or a truck or a plane or a ship, I have to carry that the entire life of the ship. So I need fuel to move it. So the smaller and lighter the power system can be and still be reliable and useful, the better it is. So one of the things that transportation electrification has done is given a new emphasis on making power systems smaller and lighter. But fundamentally, the microgrids behave the same. They have a power source. They have a distribution system. They have controls, like I said, and they need to operate reliably for the life of the vehicle. So we actually have, as we start looking at later, vehicle to microgrid or microgrid to vehicle, this is really a microgrid to microgrid connection that we're talking about. Just to prove that the one-line diagram actually has some physical dimensions to it. This is a highlight from the outside of what how the microgrid is configured. In the microgrid lab zone 2, we have a variety of inverters and connections to the grid and resistors and capacitors so that we can provide loads and buffering on the grid itself. We do have an outdoor run of the grid. This is a below ground in trenches. And this grid then it's connected into a turbine test cell where we could put in a gas turbine up to 3 megawatts and put a generator on the end of it and run. In fact, that's what you see in this picture is the gas turbine with a 3 megawatt generator on the end attached together. And we can put those in here and run those and provide power for the microgrid using a turbine genset. We also have a spin test bunker, and we use the bunker because we also provide variable high power loads. And we do that by having a 2 megawatt, 12,000 RPM motor generator, which is connected to a water brake, which is just a propeller that's being slowed or sped up by the amount of water you spray onto the blades. Now, this is controllable, so we can put variable time varying loads onto the system. And if you think about it very long, you'll understand why we do this in a bunker. If I have a 2 megawatt system that can spin up to 12,000 RPM, and then I put time varying torque on it, if that breaks, the pieces that could fly off could be lethal. And so what we do is we put it safely in a bunker so that if it ever broke, it would not hurt anybody. And I'm happy to say that we've just never come close to breaking, but we have to be careful. We also have a microgrid control room, obviously, and a place where we can put different kind of pulse loads if we needed to do that. So it's a extensive system in a series of room and outbuildings interconnected by appropriate wiring. But it's not just the wires in the hardware; it also has brains. So everything I showed you in the previous two charts gets folded into this little box down here, which says the hardware for the DC for a DC microgrid. This is set up to be DC, but it also the brains of the system are an Opal RT simulator, which allows us to simulate the behavior of our well to measure the behavior of our system, but simulate it as if it were connected to larger systems. And the additional thing that we have that's really slick is the well, this is made by National Instruments, and it's a FPGA hardware in a loop system. But what this does is this can operate at speeds that are appropriate for modern power electronics. So we can simulate the behavior of modern power electronics down at the 5 to 10 nanosecond range. But we can, it works to communicate back to the Opal RT at the 50 microsecond speeds, and then the Opal RT will give us the influence on the grid for whatever the power electronics are doing at their own speed. So we can model and simulate the behavior of the power electronics separately, but not really faster. But it's intimately connected to what the rest of the grid is doing. So we have communications back and forth between the two, and then we can put physical hardware as if it were in a more complex system and do hardware in the loop testing. So we have the 1 megawatt microgrid plus an Opal RT to simulate a power grid, plus the FPGA HIL system that allows us to look at the power electronics. And in that, using this system, we recently have done a lot of work on looking at solar farm integration. How do you put sensors into solar farms to understand how they would operate? We've also done for both solar farms and for transportation electrification fault location studies, and actually for larger grids too. We have a program right now using this whole system in the production of renewable production of hydrogen. For those of you who are not familiar with the hydrogen economy, Europe and particularly China and Japan are investing billions in this area, and the rest of the world is investing some, and I'll actually come back to an Indian investment soon. But there's a big investment in making hydrogen. Everyone wants green hydrogen, which means it's made from solar power or from wind power. And what we have a system of some electrolyzers, and we have the steam methane reformers, and we are powering them as if they were directly powered from a wind farm or a solar farm. We've been able to instrument major wind farms and send the temporal variation of the signal back to our microgrid. We then let that temporal variation drive the converters, and we then can put that temporal variation but scale it down to our size. So we can have our microgrid is behaving just like a wind farm does, or just like temporally, just like a wind farm, or just like a solar farm, but at a scale that we can use in the university to get engineering data on the variability, the efficiency declines that the various production approaches have when there's a variability in the power that's available. We've also used the system for the emulation of energy storage. If you want to store energy, we can basically take energy off the grid and make it behave like a battery or a flywheel or anything else you'd like it to be. We have stimulated unintentional islanding. When you have distributed generation, you have the potential for having part of your grid not talking to another part of the grid, not transferring power to another part of the grid because they don't need to, and sometimes that's very difficult to predict. And so we've looked at ways of measuring and identifying the unintentional islanding. So all of this is what you can do if you have a robust microgrid with the appropriate power electronics and electronic systems and computers to control it. You can do a lot of interesting and sophisticated studies. So these are the tools that we have to work with. Now that I've talked about our tools, let me talk much more about microgrids. And the first thing I want to talk about microgrids is resiliency, because one of the major reasons people are excited about microgrids, at least in the U.S., are boiled down to a resiliency argument. People want their electric power to be available all the time, and it looks like the microgrid is going to be able to help. And as I pointed out before, when we are becoming in the U.S. incredibly dependent on electricity. Everything we have in our homes, in our grocery stores, and our gas stations, and our transportation system, it's all interconnected. It's all electrical. If electricity goes away, everything dies. And so we're becoming incredibly dependent on electricity, and consequently, the dependence is developing its own set of microgrids. That the telecommunication industry has it, and data centers have it, and isolated towns have always had their own microgrids. Interesting. I don't know if any of you are familiar with the Iditarod, which is a race that they have a dog sled race they have across Alaska every year. And at one end of that is the city of Nome, Alaska, and calling it a city is very much of an exaggeration. It's a very small town with no grid connected to it, and it has its own microgrid. And its microgrid control is very relaxed. They have one person who sits there and watches what's going on. And if that operator decides that they need to have another generator online, they get up and they walk downstairs and they turn another one on. Then they come back upstairs and see if that helped. So this is not a modern bustling city, but it's very much a Wild West outpost. But it is a isolated town with its own microgrid. But now, and islands and ships and oil platforms have always been their own microgrids. Homes and businesses are becoming increasingly interested in adopting microgrid technologies for their own resiliency. Universities are doing it for the same reason, and interestingly, the universities are viewed in the U.S. as a place where one can at least go charge their batteries if there's a major charge their cell phone batteries if there's a major outage in the area. Universities are expected to stay on, and similarly, military bases are expected to stay on, but for very different reasons. A microgrid is a power grid that can operate isolated from other grids for a period of time, which may be minutes, hours, days, or years. That's not well defined. It depends upon what it needs to do. But it has to incorporate its own sources of energy, which means that it falls strictly in the definitions of distributed generation. If you're going to have a microgrid, you have to have distributed generation, and you have to have the control and the communications to balance sources and loads. You frequently have some control or some advantages of large numbers of loads that help you under control, but not necessarily. And by not necessarily, the picture I'm showing here shows a cell tower, and its power actually comes from the power grid, and its backup consists of batteries and a diesel genset that allows it to run for a week. And the picture taken here is a little more than a week after a hurricane. And the hurricane blew down the power system, so the power system was gone. The batteries ran out after about a day, and even though the structural integrity of the telecommunication system was perfect throughout the hurricane, after a week it failed, and it failed because they had that was all the longer they counted on being able to be without power. They could have developed a system that was bigger, but the engineers and the accountants put their heads together and said, a week is about right. So after a week, it went the telecommunication system came down, and it took them about 8 days, I think, before they get a truck here to give it more diesel fuel. And the reason I highlighted the hurricane is because we actually got started in this whole microgrid being important exercise with the hurricane, and in 2008 we had a hurricane that came through the town of Houston, Texas, and as it went through, we were able to go in and look at everything that was damaged and why. And one of the things that we found is in many of the areas, about 1% damage to components led to about 95% of the outages. Now, what does that mean? Well, when you stop to think about it, the reason we have this big interconnected grid is because it's a very robust and resilient and inexpensive way to get power to the people. However, it's also an excellent way of, of distributing the effects of damage. So what happens is that as you start breaking the key links in this system, suddenly the whole system collapses, and it became very, very difficult to get power. And this has inspired a lot of people to say, you know what we really need in areas that are prone to having outages for one reason or another is we need to have a grid that can disassemble itself into microgrids so that if you have damage at one point, it won't propagate through the rest of the system. And you can isolate the damage to a smaller area. You can then have a more robust system for more people. So it would be a different way of thinking about how to put together a system. And that's what started us down this track. And I said that a microgrid has to have power, and the power could be anything. It's and I think everything that I put on here is I've seen operated for one time or another. But you can use natural gas or propane or diesel or wind or solar or batteries, fuel cells, electrified transportations or buses, pickup trucks, hybrid cars, regular cars. And I know a number of electrical engineers who if when they who live in areas that have very unreliable power that have taken their standard internal combustion engine car and bought an inverter and are able to run their house off their car. This is how should I put this? This is not a general population answer because the internal combustion engines produce carbon monoxide and they will kill you. So that we can't, if you let 100,000 people, encourage 100,000 people to do this, some fraction of them are going to die because they do it wrong. And so we've got to be very careful with the internal combustion engine. But as we go to more electrified transportation with batteries and hydrogen, the chance of hurting someone uh, that way is not all that challenging. The challenge then goes back to the electrical engineers. Can I design a system that someone who knows nothing about high power electricity can plug their vehicle into their house and safely run their house? So that's one of the challenges that we have as an engineering community to understand: is there a safe way we can do this so people can use their own transportation system to provide resiliency in their own home? Also, I put down here a bonus observation. One of the things that we've also worked on extensively and became very obvious during the last time we had an extended outage in Texas is that all of these systems that we're looking at are interconnected. The power grid is interconnected to the transportation system. And think about that. And telecommunication for that matter, because the example I used the telecommunication system, we had telecommunications after they opened the road to get the diesel fuel into the telecommunication system diesel genset. So it needed electricity, but you also needed to have the roads open up. The water system doesn't work without water pumps. The sewage system doesn't work without water pumps. Modern healthcare in the U.S. can't work at all without electricity. We turned out we can't distribute food unless we have electricity. And other energy systems. So it turns out that all of these things are interconnected. And in the U.S., we don't have a good, we have a historical way of dealing with this in which we have somebody who knows each of these different systems and how they're working, sitting in the same room and talking to each other about how they can manage the whole system. Well, it turns out we have the capability today of writing computer programs that can look at these interactions, the interconnections ahead of time, and we can play what if scenarios to understand how to manage emergencies better. So one of the things that we're going to end up with by having the microgrids is that they will fit in very well with a much better way of understanding how all of these interconnected systems work together or don't, as the case may be. Oops, I am going to. Oops, my bad. I'm sorry. I can do this. Okay, now let's talk a little bit about microgrids for security. And I'm going to have to talk a little bit faster or cover a little bit more information because I'm going to fall behind. But microgrids are very, very good for not just resiliency, but also security. And this is where I want to highlight that the microgrid is different from a legacy grid. We need to change our mindset for how to handle the contingency planning for emergencies and the operation of the grid is total. We have an opportunity in microgrids to have much better control over load management for the beneficial capacity of the system. It's a smaller system, less latency, and you have the participants are willingly part of the microgrid, and one can frequent or continuously re-optimize the system to get the maximum benefit for all of the users, rather than some of them get a great benefit and others get zero. So we can actually control it in a very different way. But the biggest difference is that microgrids are small enough that we can actually model them and work the model and operate the models effectively on fairly reasonable computer systems in near real time. So what we're doing is we're driving the model rather than the system, so we can understand what's going to happen in the system before it happens, so that we don't make mistakes in the real system. We make all our mistakes in the model. The first thing we have to do this is we need a complete description of the existing system. And for that, we have to do a one-line diagram of our energy system with the electrical distribution network and all the other energy inputs. And this data set is typically not available. Every time we've done this, we have to really scratch to get the data that we need. And we realistically have to make some of it up because you can't get most operating systems, operating microgrid systems have not documented their operation well enough yet, but we're learning how to do that. But I want to stop here and make one point that will actually be important through a number of things I'm talking about. I talk about a one-line diagram of the power system, which, as I hope, as I think you would know, is something that looks like this. It tells you where the generators are, where all the cables are, and where the loads are, and gives you a way of thinking about how those interact. And generations of power engineers have been educated on how to look at those and be able to calculate and then grow, eventually develop an intuitive understanding of how that kind of system is going to operate. The next generation is probably not going to do that at all. They're going to be looking at the models. They don't care about the one-line diagram. The only advantage of the one-line diagram is to put together a model. And once I have a model, I have a much better tool to be able to understand what the system is going to do. So we're going to be going from a cadre of engineers who loved one-line diagrams to a cadre of engineers who love a model. So I think that that's something that we, as educators, need to keep in mind, and also as people who are looking at how these systems are going to evolve in the future. We're not going to be looking at one-line diagrams. We're going to be looking at the system models, and we're going to be paying much more attention to system models. And then once we have the one-line diagram leading us to a system model, what we do is we validate it using performance data. If this is a neighborhood constraint, for example, we predict how it's going to behave, and then we measure all the voltage and currents we can, and use that to refine the model, so that we end up with a model which is as accurate as we can make it. So we validate it using the data on the performance of the existing system. We then exercise the model, and this is an important part of these next two slides are an important part of the model because we can assess the performance of a phase set of improvements. If you're given the job of improving the performance of a small town like this is showing here, you can put 2, 4, 6, 10 new components in the system and know exactly how much better the system is going to perform. So you have the ability to do that, and then it becomes a decision tool for future procurements. Is it worth spending $3 million to make this change, or is it not? So I think we're going to be seeing much more on that that type of exercise. But the other point I want to highlight is in control. The model is the brain of the energy control system, and you can do other studies. I've talked about what if we change this. But the one thing I want to highlight here is it provides some cybersecurity protection. If you recall, in the Ukraine, uh, it was generally assumed that the Russians were the ones who hacked into the Ukraine power system and opened all the switches, which turned off the entire power system. They could have opened and closed them a few times and really destroyed the system, but I think they just wanted to show that they could, so they just opened all the switches. Now, what if you're driving the model rather than the microgrid directly, the order to open the switches would go into the model, and the model would say, "Hey, wait a minute! If I open all those switches, I'm going to stop working." So what the model does is sends back to the grid. The order you sent me doesn't make any sense to me. I am now going to island myself until we can figure out what we really need to do. So we have a cybersecurity buffer that can work in real time to not make decisions that may be detrimental to the system. Now, what it has to do, and the reason it has to be a microgrid, you can't just have components telling the SCADA system, no, we're not going to make the changes you say, because then the whole grid may crash. But if you have a microgrid which is designed to be able to disconnect without crashing the grid, then you can say, we're confused and we're not going to do anything until we get things straight. So let's separate, and then we'll come back together later when we know what we're doing. The bottom line from this is that everything that we're doing is getting harder. In power systems, the components used to be backward and forward compatible for 20 to 40 years. That's not happening. Everything is changing faster than that. But we still need long operating times for positive return on investment. But the technology is improving rapidly. So do we change do we get better, or do we stay old fashioned because that's the only way we can afford it? So we're going to have to understand, as we start making improvements, our modeling is going to have to both include what we have, the legacy system we have on the ground, plus the technology that we have developed since then. So we need much better decision tools going forward than we've had to have in the past when things change slowly. Okay, now let me talk very quickly about vehicle-to-microgrid. There's a bunch of there are at least 3 that I know of, groups that are looking at what I'm calling here bus exportable power. Let's assume that you want to use a transit bus to power a building in an emergency. We have one team. There was a team that put together a system of Toyota and Honda, and there's another group that is funded by the U.S. Department of Defense and Energy. All of these took advantage of the fact that hydrogen fuel cells augmenting battery power makes a really cool system to run buildings. And that's what I think all of them have looked at. It's a very simple concept. If you take a vehicle here that has a battery, you could put a fuel cell out here and possibly has an internal combustion engine if it's a hybrid. At some point, there's a connection between the generator and the motor, and you can either put the electricity in, or you can start with the mechanical power and make electricity and put that in to drive the vehicle. But you can also tap off of this and run critical facilities if you don't need to run the vehicle. So the idea is to be able to, in an emergency, you pull the vehicle up to a building and you run the building. And this actually works. Here's an example that we're running a building for part of a day. Here's a hybrid bus that has a hydrogen fuel cell running the bus. We do have an inverter and a transformer, which would typically put in the bus, but we put them out here so we can get our hands on everything so we can see what it's doing. And then we ran a multi-purpose building on the university campus for many, many hours. So this is doable. It's been successfully done a number of times. An important thing that we determined, though, by doing it and measuring everything, we determined that this actually makes sense. If your cost of power, if being shut down for a day is costing you more than $5,000, you start wanting to pay attention. If being shut down for a day is costing you less than $1,000 a day, it's probably not cost effective to do anything. But once you decide you're going to do something, you sort of have three things you can do. Uh, you can own your own backup generator, and that's what the red line shows, that it's going to cost you about this much money as a function of time to run your own backup generator. And if you rented a backup generator, it actually is cheaper to start with because you don't have the ownership cost. But after about 2 weeks, it starts becoming very expensive to have a backup generator that you've rented. The interesting thing is that if you have a, I'm sorry, that was above. This is this is the rental generator here. The interesting thing is if you have what we were using, the bus, for the first week, the bus is cheaper than anything else. It only becomes the second week that other things come in. So, and most emergencies are short compared to a week. So if you're looking at a city that has its own transit agency and it wants to keep fire stations and drugstores and et cetera available, it may make sense for them to start thinking of dual purposing their own transit systems. If you have an emergency, the demand on, at least in the US, it's documented, the demand on the transit system goes way, way down. So you have extra buses, and the extra buses can be cost effectively used as an augmentation to the power system for unique loads. And going forward, I think this is going to be much bigger. I mean, we're seeing that in the United States, the pickup trucks are being advertised now to be able to run your house for 3 days. And there's a lot of global interest in the three-wheelers in India becoming hydrogen powered. If that becomes cost effective, I'm going to be in awe because we made vehicles of that size that are hydrogen powered, and they were way too expensive. So if the developers of this can drive the cost down so it becomes competitive here, I think that's going to be a great advantage. But as soon as it is, people are going to figure out very quickly that you can also, if you're not hauling people around, I can connect this to my house or my store and generate power if I need it too. So all of this I think is going to happen. I think that what we're going to need is good engineering to make it happen seamlessly. We're going to need good education so people do it without killing themselves. We're not talking about enough power to actually hurt yourself if you're not careful. So we have to engineer solutions which are safe for the general public to use. I think the temptation to use it is going to be too big. Okay, now let me step back into hardware engineering. I've talked a little bit about what the applications are and why we're excited, but this does take some really good engineering too. And one of the things I wanted to highlight is modeling the grid connection to the grid connection dynamics. I waved my hands and said we could connect and disconnect a microgrid from a real grid, but it's harder than that. What we did is we put together a full baseline model of a microgrid and an external grid feeding it. Then we did a lot of work on validating it. We did it in both PSCAD and in RTDS. Now, those of you who are up on real-time simulation systems, I talked about we have PSCAD, but our partner had RTDS, and so we just did RTDS. It turns out, well, I don't believe any of these are particularly better than any other. Everything can be made to work. The system runs the same. So we did this with an RTDS, even though we would prefer to work in PSCAD because everything else is in PSCAD. But what we showed is that when the grid fails, and this was the grid failing at a certain point with three different amounts of power being driven, and then eventually the failure point was isolated and other plants come on, and after a long enough time, this is corrected. But what happens is a microgrid connected to this sees this failure and wants to come off and behave on its own. However, this is the simulated microgrid behavior when you had this behavior of the grid probably about 100, probably about 200 kilometers away. What happens is the power drain here, it becomes a power drain on the microgrid, drawing down its frequency, so it drops precipitously. At some point, the control system will kick in, and the microgrid will isolate. So we've isolated the microgrid. But what's happened is we didn't island it from up here in a quiescent state. We islanded it from a crash. And if we island from the crash, the recovery can get pretty ugly. And you have to engineer this transition knowing that it's going to occur. So you have to put the right components into your system to tell you to be able to protect yourself against frequency excursions that are this big. So there is engineering that's needed. It's easy to say you can connect and disconnect. The act of doing it is a lot more complex. The other thing that we have to do, we've talked about managing microgrids without, well, microgrids are not going to have the whole cadre of employees that a large company has to manage a large grid. So how are we going to manage microgrids? And what we're doing here is realizing that we can do good system design, but if you put it in the field, things are going to go wrong, and things are going to change. The demand will go up. We may not change generators fast enough. We could get large load changes. There's a lot of things that could happen. And how do we manage that in a real microgrid dynamically? Well, computers have made it possible for us to do it. Well, before that, the old SCADA system isn't going to manage this for us because the SCADA system was optimized for the large grid. It wasn't optimized for the microgrid. So we got to make something that looks at the microgrid. And here in the microgrid, we can do simulations. Again, give me something the size of a state in India, I can't simulate it in real time. Give me a microgrid, I can simulate it in real time. I have a different way of controlling what I'm doing. So and we're taking advantage of that. So what we did is we built what we call PS Secure, which is a conceptually very easy and the thing you would expect you're going to need for microgrids. Because what we do is we run simulations and we provide recommendations, but realistically, the thing that makes it work is that you have a control system on your microgrid, and that submits information to their PS Secure servers, which also have, I didn't show them here, but also have people in the loop, so that this organization will go to this one and will share its data and ask questions. What can we do? Or this one will be an oversight and say, hey, come back and say, wait a minute, you've got a problem. You need to fix this, this, and this. So either they will ask or problems will be highlighted. But this group can handle 20, 30, 40, 50 different microgrids. So you have the power engineer sitting here that can handle a lot of microgrids, and you have the technicians who are running the microgrids sitting out here. And we allow computers and communications to do the hard work for us. And for the power system requirements we have is we need a mix of sources that are working protection system and remotely operated breakers and switches. You can read that, but the one that I want to that we're really focused on is dynamic generation of one-line diagrams. Nobody knows their own system well enough, and it would be really, really good if we could figure as we're getting better and better at allowing us to infer a one-line diagram from a set of data that is good enough that we can actually make a model and operate the system. And one of the things that is obvious, it should be obvious to you that's critical, is we have to have the sensors in the system so we can understand what the sensor does. And let me take just a moment to point out that this is, well, you know it's not a novel concept, but let me show you how unnovel it is. I don't know if they showed in India the movie Ford versus Ferrari, but it was a movie about the Ford Motor Company, the Ferrari Motor Company, trying to make the best race car, and Ford managed to do it because it had a couple of people who were really good at listening to and smelling and feeling what the internal combustion engine and all the ancillary parts were doing, and figuring out how to optimize them. Today, that's a wonderful historical story, but today Formula One would laugh at that, because Formula One race cars have sensors everywhere in the vehicle, and they remotely send everything back. They have computer-based models of how the vehicle should operate, and they optimize everything all the time. And so, yes, it was wonderful in the 1960s to have somebody with a gut feeling about how to improve these, but we can do a lot better today. And that's what that's basically my view of what we're doing with the grid. It was nice to have power engineers in the 1960s who had a real good gut feel for how their power system worked. But we're going to come up with the Formula One version of power systems, in which modeling and sensing makes it able to do much better than we were ever able to do before. And the setup in the site, as I'd expect, we sense it everywhere. We have a computer that displays the information for the operator there, and then the information is sent back and forth so that there can be conversations with experts and with a larger expert system. And finally, I mean, basically what the bottom line is, this virtually gives you a power engineer available 24/7 to your microgrid facility. So, and I think this is going to be the future of the way microgrids work. There's going to be a technician who knows his or her own facility, and a oversight group that will provide good vision into how the microgrid is operating. Now, one of the other things that we end up with is you need to have a microgrid that actually makes sense on a cost basis. And I had a student who, this was what he wanted. The problem he wanted to fix is that power engineers don't have the tools to investigate the technical, financial, and environmental constraints on an optimal design. So he developed for his dissertation the appropriate software to do that. And let me put all of it up here. Basically, he looked at it from two different points of view. If you have an investor who wants to build a microgrid, if we can get enough our return on his investment, then with the output will be optimal microgrid designs and a prediction of long-term profitability, so that that will work. The other set of inputs one could look at would be somebody who says, I want to put together a microgrid which is run as much as possible off solar energy. Will it make sense financially? And from that, from that input, you come out with the techno-economic performance and benchmark based with on financial indicators. So you have you can ask this software questions in a variety of ways, and you can get the kind of answers that you need. Now, what it does is it's really just the secrets of algorithms, but it does some interesting things together, in that it will do an optimal power layout and power flow, but it will also look at cost while it's doing that. And so it works its way through a design of a system and optimizing a system, and also the risk analysis. By risk, not just is it going to fail, but how much it's going to cost. What's the probability that this is really going to make money at the end of the day? And that will benchmark the results. So it does a power system design and a financial assessment in the same software. And here's just two examples. This part over here is too small for me to look at, but this is one that he did where the optimization goal was that the present value of the system at any time is greater than the amount of money we're losing in the power losses in the system. And so the kinds of things he had to worry about were where the nodes are located, what are the routes and sizes for the feeders, what's the hourly demand at a node. So he's looking at how a power system is going to work. But he also looks at he has in it the interest, things like the interest rate and the lifespan of the project. Similarly, he looked at a different one where the goal was to maximize the amount of PV you could have in the system and still make money. And there he was looking at how much power I can generate hourly, and what's the cost going to be, what's my income, what are the key financial indicators, the key economic indicators, and the key technical indicators that will allow us to predict that this is going to work or not. And at the end of the day, he actually came out with a good prediction for how somebody could make money for a particular microgrid. It hasn't been built yet, so we don't know if it worked out, but it certainly looks good. The other thing that you have to worry about in microgrids is transient behavior. And the fundamental reason why is because they don't have the inertia that a large grid has. You don't have as many generators, it changes faster. So the control has to be different. If I have a PV plant and my solar is ramping up and down, my demand is going up and down, I have some on-site generation, the question is this stable? And the bottom line is maybe. If you do the stability calculations, let me just take this example. If you have an inertia of 1 second and a ramp rate of 2 megawatts per second, your control system has to be able to react within 1 second. If you can if you increase the inertia a little, you can give yourself about a second, 1.1 seconds to be able to react. So the three things that have to interact are pretty obvious. How fast is it trying to change? How fast can I control it if it wants to change? And then what's the inertia in the middle that serves as the shock absorber? So that's what we were able to demonstrate in a particular application. But what it also did is it made us ask the laboratory questions of what can I switch, and can I have a control system that has small enough latency that I can really make this system work? And the answer to that R&D question is yes, but the R&D was fun. What we did is we developed high fidelity models and test sequences and did experiments with diesel gensets. The bottom line is shown here. We did the modeling, we did model data, and then we did the experimental data. The people doing the work said that the reason that we did high fidelity models is because simulation can predict performance. As the laboratory director, I pointed out to them that the megawatt equipment cost me 50 cents a megawatt. So that a 1 megawatt piece of equipment costs me about $500,000, and I can't afford to replace it. So we're always going to do modeling first before we start doing high power experiments, so we make sure we don't break anything. So this is the kind of testing and work that we do. We did testing with the two 300 kilowatt diesel gensets that we moved in and attached to our microgrid. Basically, the bottom line is if we ran the microgrid from a utility source or from a generator, we could, if we did loads that were, we didn't change the amount of power we needed, we just bounced the power between two loads in the system. Stability was easy to maintain as was predicted. The same thing happens if we had two different sources. We had a small, lighter source of green, a heavier source of blue. They added up to the source on the top. We still moved the loads back and forth, switching faster and faster, and stability was not a challenge. We also did some keeping the same, ramping up a load so that we had to change the sources. We have a low power source, and then we had to kick in a second source, and then the two sources, then we had to combine sources, and we can go back to one source, and then the lower source, and that all worked too. So this was all easily done. So with fast controls, you can make fast controls, and the fast controls will allow you to do any kind of switching you want to do. But the bottom line is you have to analyze it, and you have to put it in the right control system, or you will have trouble. We also tried to do some generator block load tests, which means just dump a load on a generator. We couldn't get anything profound out of it because the generators all had their own governors and their own control systems. And since they were rented, they wouldn't let us take them off and see if we could break them. So we just were measuring the control systems that they had in them, but nothing very profound. But that is another thing that one needs to consider when he looks at the stability of a microgrid. Okay, I got through here quicker than I thought I did, so I'm going to have a lot of time for discussion if anybody wants to talk. The takeaways that I want everyone to have from this presentation is that microgrids are growing, primarily because they are financially attractive, and simultaneously, they're grid friendly. They don't require that we change the grid. They augment the grid. They play well with the existing legacy grid. And if well designed, they can enhance the resiliency of the grid, and they can. But we can make investments that improve the grid that are less costly than direct improvements on the grid itself. So the microgrids are becoming more and more attractive and more interesting. The one thing that we're going to need is that we need focused engineering on microgrids, because they have very different dynamics from the legacy grid. As I pointed out, you need faster controls because you have lower inertia and you have loads that change more rapidly. If I have something, a major city, the load changes the individual load changes may be very high, but the average load changes are very slow and very predictable. As we start getting fewer and fewer clients on the system, the load changes become less predictable and faster. And so we're going to have to do a different type of engineering. The other thing that we're going to have to look at a different engineering is that we know that these grids are going to be staffed by less experienced personnel than larger grids. And if they're going to succeed, that staffing has to succeed. I mean, one of the ways they save money is by not having to have a full cadre of a major power company to maintain a small microgrid for, 100 megawatts. It's not 3 gigawatts like a large power system. So you're going to be staffed with less experienced personnel. And if you're staffed with less experienced personnel, we can't let them fail or the microgrids will fail. And the two things that in my mind are really critical we have to make sure happen well and quickly and always. The first one is safety. If we start killing people because they are rearranging their own microgrids in ways that are unsafe, microgrids are going to get a very, very bad name, and we're going to, and deservedly so, and it will put microgrids back decades or generations. And so, one of the things that are incumbent upon us as the power engineers that are looking at these is how do we make these things safe for everybody? And obviously, one way of doing it is to go with low voltage DC microgrids, which won't hurt anybody, and then anybody can hook them up because if you get them wrong, you don't have any. You have much less risk. The downside to that, of course, is you can't do as much. You don't get as much power. You can't uh, uh, be nearly as versatile. So we're going to have to find ways of getting the inherent safety of low voltage DC into higher voltage DC and into AC systems. And I think it can be done, but I don't think it's going to happen accidentally. I think it's going to take a lot of smart people working to make it happen. The second thing that's going to have to happen is that we're not going to be able to train all of the technicians who are operating the systems to be skilled operators. They will not all get degrees in power engineering from an accredited university, but we need to be able to give them that level of support. And I think that the ability to model the microgrids provide and the fast telecommunications we have today gives us an opportunity to use remote support to really help them develop and understand and operate effectively their own systems. So we can help them optimize their systems by putting together this kind of support, and we can also help them be safe by putting together this kind of support. One of the things that this remote technical support can do is identify things that look unsafe and help people work their way through this. The fourth point that I wanted everyone to take away is that the microgrid is a natural partner with transportation electrification. As they share common technologies from DC to DC converters to wide bandgap semiconductors to advanced insulation systems. The big difference is that transportation electrification puts a larger premium on the size and weight. In fact, I was fascinated to read just a general purpose magazine article which talked to half a dozen designers of electric vehicles and asked them to identify the 3 or 4 things that they saw were the largest engineering challenges for transportation electrification, and all of them had as number 3, 4, or 5 the weight of cables. They all want to get the weight of cables down. We have to get the power system being smaller and lighter for cars, trucks, buses, airplanes, every place. So there's going to be a lot of effort to understand how to design power systems that are smaller and lighter, but they're going to be microgrids. So there's going to be beneficial transfer of information from the microgrids to the vehicles. And in my definition of a microgrid also includes a vehicle and a house or a store. Because when you start connecting those together, you then have power sources and loads and distribution, and that gives you control issues. And we need to understand how to work on that scale. That some people like to call it a nanogrid, but to work on a very small scale up to the 100 megawatt or so, there are going to be different kinds of problems and different sorts of issues. But in each of those, we need both technical support and we need to make sure we're safe to have so that we can get both transportation, electrification, and microgrids to grow together and be successful. And finally, I'm absolutely convinced that achieving success requires a global effort. And you may be able to convince me that the technology is already global. We can buy it anywhere in the world from the same sets of companies. But the real reason why it takes individual effort everywhere is that all of the applications are local, and therefore to be cost effective and effective, you have to take into account what legacy system you have. Now, if you're taking a place that has been totally off grid and giving it some power by sticking up a solar panel, that's one thing. But if you're trying to augment a quasi-developed area and make it a more developed area by layering in a microgrid, you have to take into account the technology of the microgrid plus the technology that's there, and that takes excellent engineering to be able to make that a success. And that engineering is local. That's not somebody writing a book somewhere saying, this is how I would do it. This is smart people taking a look at their own challenges, their own problems, their own constraints, and optimizing within those. And with that, I hope that I have generated some interest in your hearts and minds about microgrids and their future, both the engineering challenges, the financial advantages, and the beneficial societal impact that I think these can have. And I'll be happy to discuss any of these as much as anyone would like to. Thank you.
Thank you very much for a nice presentation, sir. And definitely it will motivate the participant to work in the area of DC microgrid as well as for the AC microgrid. And now I would like to invite my colleague, Dr. Subbu Upadhyay, to take the question, to discuss the question with the expert. Dr. Subbu.
Yes, thank you, Professor Robert. Thank you, Professor Robert. So the discussion was very means we have learned many important things. Some of the few questions are there that were asked by the participants. First was how much time the transients are allowed while islanding of microgrid.
That's a very good question. It really depends upon the technology that one has for islanding. Typically, it's going to take some seconds with the hardware that we have available today to identify unambiguously that something is happening in the external grid, to convince yourself that it's safe to operate the microgrid, and then to take the action. So it's going to take probably seconds, and I explicitly put that you need to take time to make sure that the microgrid is ready for the transition, because we had a spectacular example of that not being true in the United States. Everyone is excited about microgrids because when Hurricane Sandy hit the east coast of the United States, the microgrid at Princeton stayed up and all of the grids around it went down. So the answer was yes, microgrids are wonderful. But earlier during a blackout event where a power grid was failing, the University of Maryland microgrid looked at the frequency drops going on the grid outside and said, the outside grid is failing, I have to disconnect. Unfortunately, they hadn't engineered the disconnection well enough during that failure. They didn't have enough power to be able to disconnect, and they immediately went down. It turns out the local utility was able to recover, so the only person who went down was the microgrid, and everybody else stayed fine. So you have to have enough time to I was going to say, to think about. You don't really think about. You have your computers decide if it's safe to make the change, and then go ahead and make the change. So yes, it's going to be seconds.
Okay. Yes. The means whenever load setting will occur, it will be generally due to the low inertia condition, I think.
Yes. Yes, it is due to the low inertia condition of the microgrid. That's why you don't have much time.
And since whenever we are going for means ships like that transportations and basically ships, these ships are basically operating in islanding mode. So whenever they are operating in islanding mode, there needs to be some backup source to supply it. So in such conditions, if there a failure may occur in the system, so how to cope up with that?
Yeah, that becomes a very interesting cost engineering issue. You would typically in the U.S. we always plan for two contingencies. So if something fails, we have something else that's there. We can't ever fail the whole system from a single failure. So it takes two failures to do it. But we seldom plan for three. Now, when I'm running a microgrid, I'm assuming I have a prime source of power and I have the grid. And if one of those goes down, I still have the other. But you're absolutely right. At that point, if we're going to be operating at any time in that mode, we need to have a third source because we no longer have our two sources of power. And most people are not worrying about being that secure yet, but I think that we're seeing some in some very high value places like data centers and possibly military bases that are starting to look at, rather than go too deep, they want to go 3 deep for electric power because power is that important to them and they need to have 3 different sources. But this is actually where transportation electrification can come in. If I happen to have a fleet of vehicles at the same place that can be used for power, they can help ride through a shorter term issue if the other two systems, if your grid and your prime system and your microgrid do not work. And we saw the example of this. I mean, I'm not making this up. The example of this was at the Fukushima plant in Japan. When the tsunami hit, the folks in the control room lost power and they couldn't control their reactor. And they all ran out the parking lot and pulled the batteries out of their cars and rigged up a system to be able to do it. This is an elegant, well-engineered equivalent of that. Rather than pull the batteries out of the cars, you just design your transportation electrification so that you can plug it in the grid so it can provide your third source. So I would hope that is what it goes to. But if you need something faster, sooner than that would be available, then you're probably going to have to start thinking of what other sources do I have. I know one other thing. I know a lot of folks in the U.S. are looking at how they can balance using solar and wind and a fossil fuel plant to adjust their load to say, okay, how long is it going to take me to refuel the fossil fuels? What's the weather going to be? How much power can I afford to use in a given time? So there are people who are worrying about this. Yes.
My last question is that regarding the cost versus event distribution that you have shown. So I like to understand more about it.
About the what distribution?
Means curve that was shown in the slide that was between cost versus event distribution. Means some large distribution was there. Along with that, some DGs may be there as a backup source. I think cost versus means time management, how these different systems are operating. So there was some graphs, one graph that was shown.
Oh, I know what you're talking about. That was for the for using buses as backup. If I use buses as backup, then it would show there were 3 different assumptions we looked at. One was a diesel genset that was owned by the facility, so that would be a hospital or a data center. The second one that we looked at was a diesel genset that was rented for the duration of the event. And the third one was if I set up my transit bus so we could just pull in and do the job rather than one of the diesel gensets. And we looked at what the cost would be of the using the transit bus and what the cost would be for the other two. And it turns out if your time is less than a week, the least costly is to use the transit bus. And primarily because it's used for something else all the other time, so you don't have to amortize the cost when it's saying you're not doing anything. And you know it's working because you just used it yesterday to run a bus route. So it makes people a lot more comfortable when they are doing this. But if you are if I own my own diesel genset, I have to continually exercise it to have confidence that it's going to work when I need it. And so that's a cost that comes in that has to be uh, uh, considered when you consider owning your own diesel genset. So the only point that I was making with the costs there was that for short times, which are about a week, it looks like with the data that we were able to gather, that using a transit bus as a power source for a single building is probably less costly than renting a diesel genset or owning a diesel genset. If you do it longer than that, then yes, you want to have your own diesel gensets. But for short term, it may make a lot more sense just to have the transit bus being able to provide power. And I should point out that that's really something that I'm pushing here in Texas, because I don't know how much I don't have any idea if the news of our 3-day blackout, how far, if anybody else cared about it, but we had a 3-day blackout that really surprised us. And one of the reasons we had the blackout is because we were supposed to have rolling blackouts, where if you had that everyone would be out for 10 or 15 minutes, and then they'd be on for 3 or 4 hours and off for 10 or 15 minutes again, which is a tolerable way of doing things when things are cold. But what they found out is the amount of power they needed to cut. They had to turn off every circuit that did not have a priority load on it. So everybody who was not on a priority circuit was cut off for 3 days because they couldn't do a rolling blackout. And it turns out if I could take those priority loads and power those with a transit bus, it enables me to then give everybody power a fair amount, be off and on a fair amount of time, so that people's pipes wouldn't have frozen and people would not have been, people would not have frozen to death. We had people die in the dark because they got too cold. So we could have fixed all of that by using the buses just to power the critical loads. So that's that's why we're really pushing for this idea of now we can do the same. Now let me put that. Be very honest with you. We can do the same thing by just putting a diesel genset on every critical load, which is what the diesel genset manufacturers want us to do. But the problem is that costs more than using buses or trucks to do it. And particularly if you're worried about a fire station, I could use a fire engine as the truck to power the fire station. And if it turns out they have to go on a call, we can let the fire station cool off for a while. And when they get back an hour later, they can heat it up again. So there are a lot of ways of using electrified transportation and the grids together to do something better than either one can do by themselves.
So another question that was asked by the participant, role of aggregator in microgrid, how to manage the communication between utility and customer.
That's a great question, and it's also a philosophical question in my mind. I don't like aggregators. I don't think we're going to need them. I think that we're going to have a good enough telecommunication system that I can do a reliable, transparent data set, and that the utility can look at the data, and the consumer can look at the data, and the microgrid operators can look at the data, and we can all have that same data set and make the best decisions on the data set, and nobody needs an aggregator. I think an aggregator just takes money out of the system for minimal value add. Now, I will confess that not everyone agrees with me. They think that this is going to be harder than I think it is. But I just think that we can have sufficient transparency in the data in the operation of the system to those who have a need to know that the role of the aggregator, I think in the future, in the far future, is going to be very low. In the short term, we will probably politically put aggregators into a role. We keep talking about them in the U.S., and I hear about them in other parts of the world. And I think the reason that they're growing slowly is because a lot of people recognize that it's probably only a short-term benefit. And as we improve our data reliability and our communication, we probably don't need them. And so it's going to be an interesting question of how much we really are going to need the aggregators. But they can play a role, yes. I mean, this is I will put that as a very personal opinion. I happen to not like aggregators. If you are an aggregator, I love you anyway. But I think it's going to be a short-term job. I think it's going to be one of those jobs that I think technology will make go away over time.
So with this important information, I like to give the vote of thanks to our keynote speaker, Dr. Robert Hebner, professor of University of Texas at Austin, USA, for enlightening us on the topic of learning to love microgrids. Ask the coordinator of this FDP, Dr. Rajiv.
Okay. Thank you, Dr. Subo. Sir, this is the e-memento from our side. Please accept it.
Thank you very much. It looks very impressive.
Yes, sir. And this is e-certificate. I will send it by email to you, both the copies.
Thank you. This is very nice. And I enjoyed giving the presentation. It was this is a topic that obviously is near and dear to my heart. So I hope that I have inspired some of you to work in this area too, because we need all the help we can get.
Yeah. Thank you. Thank you very much, sir, being with us. It's really a great pleasure for us to have a speaker like you. And you are one of the eminent speakers from the US. I have attended many meetings. I have worked with you, so I can understand that how much deeply you have worked from the different perspectives in the area of microgrid for the military ships you have worked, and you have a very microgrid in the megawatts. In India, we have the microgrids, but main focus is here towards the buildings and the campuses level. But I have got the lot of exposure in your lab. So thank you very much, sir.
Thank you.